Welcome back to ECE 442, 542. Yes, we all have to wave. That's fine. We'll do the wave and see what frequency that is, and maybe we'll do some filtering on that wave. Homework number 6 is due on Monday. Exam number 3 is a week from today. We will have a review session on Monday. And there is review material for exam number 3 posted on D2L. And if you have a topic or questions that you want addressed during the review session, I've posted a quiz, which is really just a way for you to type in an answer, or I'm sorry, a question and the answer if you want, but we'll see if I can incorporate that into the review session on Monday night. Today what I want to do is go through the root locus. We sort of showed where that might come from. It really comes from the characteristic equation, or the characteristic polynomial set equal to 0, or the denominator of our transfer function. And that gives rise to two different conditions, a magnitude condition and a phase condition. And all of the root locus rules that we will discuss revolve around those two conditions. We'll look at some examples. We will numerically compute the roots. You could actually just plug in different values of k and have your calculator show you where the roots are to generate a root locus. We will generalize the notation, and then we'll start going through some examples that help illustrate the rules for sketching the root loci. So here is our classical block diagram, and now if there are poles and zeros in the controller, I've collected those into the plant, and that combination of controller pole zero factors and plant pole zeros have all been collected into what I'm now labeling G bar. And I factored out the adjustable parameter that we will be using, and that one I'm calling K. So the adjustable parameters are K, and everything else is pulled into what I'm calling G bar. And with that, we've already talked about different types of root loci. For example, here are two different cases. The first case, and what are some ways of thinking? The red line or lines indicate the root loci construction, or the actual root locus diagram. In the one on the left, if you look at that, you should immediately see, oh, I have one pole, and that pole is at z equal to 2. And now you could start asking the question, how many poles do I have? How many zeros do I have? What's my pole zero excess? And based on that, that will give you information as to how to sketch the root locus. In this case, you have one pole, no finite zeros. What's your pole zero excess? How many more poles do you have than zeros? You have one more pole than zero. And now you can start asking, based on the phase angle condition, the points on the root locus have to have a phase of 180 degrees. You have one pole, so essentially if you view that real axis as an infinitely long loaf of bread, you're just cutting that bread into in half at the pole location, and you're asking which of those two real line segments belong to the root locus. Do both of them? Do any of them? Or just one? And you can now stand on one side of that pole and ask, what's the angle from that pole to this location? And if that angle is 180 degrees, then you know where you're standing belongs to the root locus. On the one on the left, the one pole system, if I stood at the origin and I said, if I isolate a point, let's say at the origin, and I stand at the pole and I say, what angle do I need to turn through to get to that point, the origin, I can see that I'm turning through 180 degrees. So all points to the left of that pole are on the root locus. Similarly, with the diagram on the right, how many poles do we have? There we do have two. How many finite zeros? None. So our pole zero excess is 2, which means that we also, and we'll talk more about this, we have 2 zeros at infinity, which means we are going to have 2 branches of our root locus diagram going off to infinity. And where infinity is depends on how many more poles we have than zeros. If we have 2 more poles than zeros, our infinity is located at plus and minus 90 degrees. Or the fundamental angle will be 180 divided by that pole zero excess, or 180 divided by 2. But in this case, we have our bread, and how many real line segments can we identify for that particular collection of poles and zeros? How many real line segments? Not how many belong on the root locus, but how many real line segments have we chopped into? 3. We have 3 sections. Segments is the rightmost segment on the root locus. No, because all the angles from those poles are 0, so it's not 180. If I'm standing between the poles, between 0 and 2, I now have one of those poles contributing 180 degrees. The other pole is contributing 0, and so my net angle is minus 180 from those poles. So the middle section does belong to the root locus. And the leftmost segment, if I now look at a point, let's say minus 1, and stand on both of those poles and find the angle each of those poles has to turn through, the pole at 2 has to now rotate that much to see at minus 1. The pole here, I'm measuring my angle with this virtual horizontal axis, and now, so I have 2 turns of 180 degrees, which added together gives me 360, which is not 180. So those points over here do not belong to the root locus. We need each point that's on the root locus to have an angle of minus 180. And we'll go through that one again a little bit more. But now I'm just trying to illustrate how more interesting these patterns can become. The one on the left now in the second row, how many poles do I have? 2. How many finite zeros do I have? 1. What's my pole zero excess? 1. So now how many zeros at infinity do I have? 1. So that means I'm going to have one branch of my root locus going off to infinity. And when I just have one, it's going to be at 180 divided by 1, or at 180 degrees. So one of my branches of my root locus is marching off to minus 180 at an angle of minus 180. And how many real axis segments have I now created by this pattern of poles and zeros in this system? I now have 4, don't I? I have 4 real line segments that could possibly belong on the root locus. And what you will see is if you're standing in one of those 4 sections, if you look to your right, and if there's an odd number of poles and zeros to your right, then that segment will belong to the root locus. Let's try that out. So here, if I'm standing to the right of 2, let's say I'm at z equal 3, is that going, and if you look at all of the angle contributions to that point at z equal 3, all of them are contributing 0 degrees. So that segment from z equal 2 all the way up to infinity should not belong to the root locus. If I now squeeze in between 1 and 2 somewhere, now if I'm, let's say, at 1 3/4, what's the angle from 2 to 1 3/4? It's 180, isn't it? What are the angles of the other 2, pole and 0? 0 degrees. So now I have a net 180 degrees between 1 and 2. So that real axis segment does belong to the root locus. And there's an odd number of poles and zeros to the right of any point between 1 and 2. What if I position myself now between the origin and 1 and I say, is this segment on the root locus? Now I have two poles that each contribute 180 degrees. The 0 contributes 0. The sum of all of that, the algebraic sum, is 0 minus 360, or 360. So those points between the origin and 1 do not belong to the root locus. Finally, the fourth segment is to the left of the origin, and now I have 3 poles and zeros, and that's now this odd number. I have an odd number of poles and zeros to the right of any point in the left half plane on the real axis. I'm going to have 180 degrees of contribution. I have, let's say, from the pole at 2, I have 180. From the pole at 1, 180. From the 0 at the origin, I have 180. So I now have 180 minus 180 minus 180, or a net minus 180. And we will learn how to sketch this. In this particular case, when we have two poles to the right of a single 0, we actually have a circle that connects off the real line those real line segments. And we'll figure out how to determine where it breaks away. This is what we will call a breakaway point, and we will call this point the re-entry point. When does it re-enter the real line segment? The fourth example, how many poles do I have? In the lower right-hand corner, the second row, second column, plant, I have 3 poles. How many finite zeros? 1. What's my pole 0 excess? 2. So where are my zeros at? How many zeros at infinity do I have? I have as many as I have a pole 0 excess. So I now have 2 zeros at infinity. They're going to be going at 180 degrees divided by 2, or plus and minus 90 in this case. Two more. And now can you see the way the patterns change, even though in the third row left column, how many poles do I have? 2. How many finite zeros? 1. Well, that's the same number of poles and zeros as the diagram just above, but do the diagrams look the same? No. And it's all based on the relative locations of the poles and the zeros as far as how we sketch. So in the third row left column, how many zeros at infinity do I have? 1, because that's my pole 0 excess. I have a pole 0 excess of 1, and that's going to be having an asymptote, or a branch of my root locus, going off at an angle of minus 180 degrees. Likewise, for the third row rightmost, I still have 2 poles and 1 0, but now look at the direction that some of those branches are headed. I'm always starting on my poles, and I finish on finite zeros and zeros at infinity in terms of the red branches of my root locus. And I hope now you're starting to think about, how can I determine this structure of my root locus? What do I need to do, or how can I sketch those 6 patterns based on the patterns of poles and zeros in my system controller combination? Here's a different system. What's going to determine the dynamic behavior of that system? Now I'm showing you. If you found the closed loop transfer function between R and Y, that's our cheer. That's kg over 1 plus kg. You plug in the k, that's just a constant, and you plug in the g. I now have a pole at the origin and a pole at 3/2. And I work all of that through, and basically now the numerator of my denominator, is that making any sense? So now I have a ratio of ratios, correct, in my T sub C of Z. I have a ratio in the numerator and I have a ratio in the denominator. But what governs the dynamics is the numerator of the denominator, the 1 plus kg of z. I'm wanting to know, when does that vanish? When does that equal 0? Well, it equals 0 when the numerator of that expression vanishes. So if I start talking about the numerator of the denominator, that's what I'm referring to. But that's what we're using. We're using this formula, 1 plus k g of z, and in some cases now we'll be looking at what's the numerator of that g and what's the denominator of that g. Those are my finite zeros and my finite poles, respectively, when we're sketching these root loci. What we're interested in now is how do the closed loop poles behave as I vary k between 0 and plus infinity. I want to know, how do the roots of this polynomial change as k varies from 0 to infinity? How many roots do you have? How many open loop poles did we have in g of z? 2. How many closed loop poles do we have? 2. So we have 2 branches of our root locus that we have to worry about, or that we will be sketching. Our closed loop poles, again, are governed by 1 plus kg of z. But if we now set that equal to 0, what we're interested in now is the fact that the numerator is what influences when that equals 0. And if we focus on the numerator of 1 plus kg of z, the original denominator is now the z times z minus 3 halves, the first factor in that expression, plus k times the numerator. And the numerator was very simple. It was just a constant of 1. It could be a constant of 30, or any kind of constant, or it could be a 0 factor. In this case, it was not. We want to know now, I have a second-order polynomial. How do the roots of that equation change as I march k, or turn k, from 0 to infinity? That's what the root locus diagram is giving us. So if you have a calculator, if you have MATLAB, you could simply stay up all night and plug in different values of k, find the roots of that, and you would have your root locus in terms of numerical values, without memorizing all of these rules. But it's nice to know the rules. But this is another way of thinking through that process. And here's what results. If you sit down, maybe I didn't stay up all night calculating, but now I just wanted to do some different geometric symbols. I now have a square, I have a triangle pointing up, a triangle pointing down, I have a diamond, and I have a plus sign. And now for all of those symbols, I'm trying to show how those symbols correspond to a particular value of k. As I'm incrementing k, or increasing k, I'm going down in my table of numbers. So with k equal to 0, what are the roots of that polynomial? Well, they're the values of z that cause it to vanish, and those are just already factored. One's at the origin and one's at 3 halves. That's what happens at k equals 0. So I'm starting when k equals 0 at my open loop pole locations in the root locus. What happens now if I plug in 1/4? Well, if I plug in 1/4, plug that into the quadratic formula, I compute now a pole at 0.19, and that's where this square is supposed to be, roughly. This square is now at 0.19, and this square is at 1.31. You see that I'm now moving towards each other as I start to increase k? That's what happened when I was at the square. What happens when I'm at the triangle? Now I'm at the triangle. I've cranked up my k to 1/2. If k is now 1/2, now if I do the quadratic formula, I end up with one of my roots being 1/2 and the other root being at 1. which, if I just follow those in, I'm now at 1 and 1/2, and that's now where I'm located in my root locus. I already knew that that segment of my real line was a part of the root locus diagram by cutting my bread and doing the phase angle condition, I hope. I hope that I already knew where my root locus was living. If I crank up my gain now to 9/16, I now move to actually where they're right on top of each other. I have two real poles right on top of each other at 0.75 and 0.75. And if I keep cranking up the gain K, they can't just stay there. They actually have to move somewhere. And that's going to be based on the pole zero excess. How many more poles do I have than zeros? Now they have to move off of the real line. And since there's no more real axis segment that belongs to the root locus, I can't come back to the real line once I've departed in this particular scenario. And my angles that I will be moving at will be 180 degrees divided by the fundamental angle will be 180 degrees divided by the pole zero excess. Yes. The arrows represent the direction of increasing K. So as I increase K, my closed loop poles are moving in the direction of the arrows. So the pole at the origin is moving to the right. The pole at 3/2 is moving to the left. And as I crank up K, and if I get to 9/16, now they're right on top of each other. If I crank it up a little bit more to 3/4, I've moved off the real line, and now I'm up to the diamond. And if I crank it up some more, if I crank up the gain K to 1, now I'm at the plus sign. Is that making sense? Now you know how to numerically check your work. I keep teasing people and say, did you check the answer in the back of the book? You have a lot of different ways, and that's what you'll have to do when you are out of school. You won't have the back of the book, but you need to create the answers in the back of the book yourself. And this is one way to do it. If you have a calculator, for example, you could have done these commands. I know it looks crazy, but it's just complex zero. You can't do zeros because then if you have complex roots, it'll stumble. It'll say, oh, these roots aren't real. So you say C zeros, complex zeros, and now I'm simply putting in z squared minus 1.5z plus k. The vertical line says, and now plug in k equal to 0.25, and I want to find the values of z that cause that equation to equal 0. And the answer ends up being 0.19 and 1.31, which is what I had in the table before, for a gain K of 0.25. This is just one other way of illustrating how you can check your work or determine the answer in the back of the book. And it really doesn't get any more difficult if this was a higher order polynomial. The strategy you could still follow. If you don't have a TI-89 or an Inspire, you could use the quadratic formula. Yay! But if you have it, you might as well use it, right? So if your parents or you have invested that money, you might as well figure it out or know how to use it. So now what I want to do, yes, question. Yes. So now the question was, if we were asked to find the range of K, and then you stopped with your question. So what are you wanting? The range of K for stability? So now how do I find, and I didn't do that, did I? The question was, what's the range of K for stability, which is probably a homework problem. How do we determine the range of K for stability? Have I given us any kind of hope in where that might, or how we might find that range? Yes. So now the stability influences the unit circle, or is impacted or determined by the unit circle, correct? So now what you're doing is you're virtually saying, I don't know why I want to get, there's a quarter of the unit circle. Now what we're trying to do, and maybe to emphasize it, I would do this. But do we initially start with the branches, or if the system is stable, then we need all of our poles, closed loop poles, to simultaneously be inside the unit circle. In this case, how many poles do we have? Two. We have two closed loop poles. Do they initially start both in the unit circle? No. So we know that at k equals 0, that's not in our range of stability. But does it look like at some point they both will simultaneously be inside the unit circle? What happens at the triangle location? The upward pointing triangle. The one on the right now has reached 1. What about the one at the origin? Does it go off or outside the unit circle? No. So that now gives us our lower limit. So what was the gain k to get us to z equal to 1? That's in this diagram, that tells us our lower limit on stability. In this case, we would say, oh, to get to 1, we needed a gain k of 1/2. So we need to crank up the gain k at least to 1/2 to get us to the point of being stable. Is that clear? Now, can we just crank up k to infinity and remain stable? Do our branches always remain inside the unit circle as we increase k? And hopefully this diagram illustrates no, they do not. Now you can see that in fact they actually leave, and I actually think they leave at the plus sign. But you could find that, you know the real part is 0.75 because that's where they're breaking away. Maybe you don't know the y value, but you could say, oh, I know it's at 0.75 plus y, I'm sorry, yes. So let's say this point here, let's say we didn't know what it was. We would say, oh, this is at 0.75 plus j, let's say y. But what do you know about that point? You know the magnitude of that has to be 1. You could now find the magnitude of that when it's equal to 1, and you now know that point. Or you could find the gain, k, to make you have a magnitude of 1 at that location. And I believe it will be this plus sign, which now a gain k of 1 would give you, if you found the magnitude of 0.75 plus j 0.66, maybe that equals 1. It's close enough. So now we know that our range of k for stability is what in this case? For stability, it's now living between 1/2 and 1. Did that answer your question? And that's the thought process you really want to be using. It's nice to sketch quickly a root locus and say, oh, is this making any sense? Is there any range of k possible where all of my closed loop poles are simultaneously inside the unit circle? And what we are going to be doing as engineers is making sure that the dominant poles are where we want and the others are faster than that. What are the dominant poles? Let's say I had four closed loop poles in my system. Now I'm going off script. So I'll just introduce some more paper. But let's say that we now had 4 poles. And these, let's say, are the closed loop poles. which of those four poles would influence the dominant behavior of the system? Are the ones closest to the origin the dominant poles? What influences the dominant, or what, and by dominant, I'm meaning those are really the slowest poles, correct? The slowest poles are going to dominate my response. And that's what you're wanting to then meet your design specifications. The other poles you would want to be faster. So what we will possibly do in this class is we may pick two that satisfy our design specs and then locate all the others conveniently at z equals 0, at a fast location. In this case, the dominant poles in this picture are now those two. And you would be worrying about their radius, their angle, and their heart to give you settling time, peak time, and percent overshoot. All right, now where were we? We were trying to generalize this idea of sketching a root locus. Suppose now that somebody gives you a plant, g of z, that's 1 over z, z minus 2, and then they say, oh, I have a controller that has a 0 at the origin, and it also has a pole at minus 1. Terrible controller, but we'll just leave it at that, okay? And now we want to know, how do we set this up so that we could sketch a root locus diagram that would tell us where our closed loop poles are as I adjust the gain k from 0 to infinity. What we are going to do is we are going to essentially push all of our poles and zeros into one block we will call G bar, which will now have our numerator N and our denominator D. And if I start talking about open loop zeros, those are the values of Z that cause N of Z to vanish. Little n of Z, and those correspond to G bar. If we talk about open loop poles in the root locus discussion, those will be the values of Z that cause little d of Z to vanish. Those will be our open loop poles. Our open loop zeros and open loop poles are roots of N and D respectively. Terminology clear? And we've now isolated K. What we want to do is now sketch the root locus, and conveniently for us, what happens to that common open loop 0 at the origin and the common open loop pole at the origin, they cancel each other out. And now we're left with a root locus that's going to be influenced by a open loop pole at 2 and an open loop pole at minus 1. And we want to know, based on those locations, if we now adjust K from 0 to infinity, what are the closed loop poles going to be? How many branches of the root locus do I have? Or, so now you have to kind of be clear and always ask me, maybe I wasn't very clear, how many real axis line segments are there? You could say 3 or 4. It's either one, because that pole 0 cancellation, it kind of makes one go away. So I would probably have to count 3 or 4 as a correct response, depending on how you interpret that pole 0 cancellation. But really, that pole 0 cancellation is like erasing that pole 0 pattern effectively. They cancel each other out. And when can we cancel poles and zeros? Inside the unit circle. You never, ever, ever want to cancel a pole or a 0 that's outside the unit circle. Is that clear? You can place poles or zeros outside the unit circle. We may have to do that. but don't place them in a location that will cancel a pole or a zero. It's smart sometimes to cancel poles and zeros inside the unit circle. It simplifies your analysis, but never, ever, ever cancel poles or zeros outside the unit circle. Pardon? So the reason is explained in the controller design overview lecture for not canceling poles and zeros outside the unit circle. That's in the supplements to Unit 5, but in short phrasing, it basically will lead to unstable or unbounded signals inside your block diagram or inside your system. Maybe not between the reference input R and the output Y, but maybe between the reference input and the input to the system, or the disturbance input and the output, etc. You might have an unbounded signal existing in your system. Pardon? Why did I make the pole at -1 and 3? What? Oh, I have no idea why I made the pole at, so now you're going to make me correct my coloring, and this is playing with fire. There was no significance to a green pole. It should have been blue to be consistent. The question was, why is there a green pole at -1? It threw me. I didn't know what the question was. Good question. Any other questions? But now we have, do you see now how to create this root locus? This structure of a root locus you should be able to do in your sleep now. When you have two poles and effectively nothing else, what's going to happen? They're going to come together, they're going to meet halfway between each other, and then they're going to go off at plus and minus 90 degrees. And now you could compute, without doing anything real fancy, you could find the average of those two locations, and that's where they break away. Question? So the question was, what would the root locus look like if you had a pole and zero canceling each other outside the unit circle? That should never, never, never happen. So, but it basically, you would unfortunately not see anything. They would cancel, and so you would be misled to thinking everything was okay. And that's the fallacy or the myth behind canceling things outside the unit circle. You think, oh, everything is fine now, but it's not. You could have unbounded signals somewhere in your system that you aren't aware of during your design. No, the question was, what happens when you cancel a polar zero outside the unit circle? And I would just say, don't ever do that, okay? Because the math will, if you work through the math, you will see that you now have unbound and not a bounded input, bounded output transfer function somewhere in your block diagram. The math will show you that. But we won't be going through that here. Now, we found how to find the root locus for some of these trivial, or maybe not trivial, but some of these basic cases. All of these root locus diagrams come from this one equation, 1 plus k g bar of z equaling 0. And if we now rearrange that question, oh, how did I get this k, the range of k for stability? How did I get the k for stability? This is now similar. It's obviously different than the last problem, but the logic is the same. If you look at the root locus, do you start with both closed loop poles inside the unit circle with k equal to 0? You start with one out at 2 and the other one at -1. So one's okay, but the other one is not. You now have to figure out what's the gain k to get me to 1. And we'll hopefully show how to find that, calculate that in a minute. But we'll find that, and it will be 2, the gain k to get us to 1. And the other one that will sneak in and stay a little bit further into the unit circle. Then we will find that the upside down triangle is a gain value k of 3, and beyond that, we're outside the unit circle. So the stability region for this particular case is going to be between 2 and 3 for this choice of poles and zeros and gain value. Question? So the question is, do we want to put a closed loop pole right on the unit circle? And for those of you listening to this, you have no idea what just happened. But if you put something on the unit circle, what's going to happen? If it gets excited, if that mode gets excited, it's just going to sit there and shake, right? And it will never damp because it's not inside the unit circle. So really, in reality, you probably want to be somewhat inside the unit circle for your dominant poles or all of your poles. If you locate something on the unit circle, no, you probably don't want to have that happen. Right? All right. Hopefully nobody caught that. But hopefully you'll never forget that, right? You shouldn't put anything closed loop on the unit circle. But if we rearrange 1 plus k g bar of z equaling 0, we will solve for k g bar of z, and that ends up being equal to minus 1. But minus 1 has a magnitude of 1 and an angle of minus 180. And that magnitude and angle information is what we use to derive all of our root locus rules for sketching the root loci. The magnitude of this product, the gain k times g bar, that has to be 1. And we'll use that to find k at different values of z. We also know that every point on the root locus has an angle or a phase. Algebraically, we take all the poles, all the zeros, angles together, and they have to algebraically sum to minus 180 degrees. As an example, and hopefully here all of my poles and zeros are blue. Hopefully all of my poles and zeros are blue. So they are. I have 4 poles and 1 zero. But to find the contributions from each of those, we have this virtual horizontal line, and relative to that, we measure the angle to a spot in the complex z-plane. Remember last time I was running to different locations, and I said, am I on the root locus? Well, now if I run to star, I need to compute the angles from all of those poles and all of those zeros and determine if algebraically they end up giving me an angle of minus 180. The angle from the zero, what is that? Now you might want your protractor and you might want a compass to sketch these. Again, we're drawing, and your parents will go, what are you drawing? A root locus diagram. Then they'll pay attention, huh? So now, yes, they will. So they'll say, where are your closed loop poles? For what value of gain k is your system stable? But here, the angle of the zero to that star is about, what, 45 degrees? And that's what you would have for theta of z. You could get out your protractor. If your units, if your axes are equally scaled, then your angles will be accurate, and you could physically measure those angles, or you could compute those analytically using trigonometry. And you have now all of these angles contributions from the poles. You have theta P1, theta P2, theta P3, and theta P4. You have all the sum of the zeros angles minus, because the poles are in the denominator, you're subtracting all of the poles angles. And if those end up being equal to minus 180, then star would be on the root locus. Yes. Yes. So we always have zeros we'll add up all the zeros angles, their contribution, and subtract all of the poles angles. And which poles and zeros are those? Those are our open loop zeros and poles. The zeros of n of z and the roots of d of z in our capital G bar of z equation. Now, is everybody ready to read a novel? But you can come home and read this. You don't have to write it. But now I want to write down some of these rules. What? So rule number 1, root locus construction rules for n of z and d of z. The root locus branches start at where? The open loop poles, and they end at the open loop zeros, finite zeros, and if we have zeros at infinity, how many zeros at infinity do we have? Equal to the pole zero excess. We'll have that many branches going off to infinity. So far, we've really only talked about 2 infinite zeros, and those branches go off at 90 degrees and then minus 90 degrees, or 90 and 270. If we had 3 poles, if we had 3 zeros at infinity, then the fundamental angle would be 180 divided by 3, and the first angle would, or asymptote, would be going off at 60 degrees. The next one at 180, the last one at 300. But this is rule number 1. And I think we've already described that. Rule number 2. So this is the starting and stopping location of our root locus branches. How many root locus branches do we have? How many branches of the root locus do we have? We have the number equal to our open loop poles, right? And those will be the number of open loop or closed loop poles. So if we had 4 open loop poles, we would have 4 branches. What's maybe confusing is sometimes one line segment might contain 2 branches. We've already seen that in some of these cases. So don't let that confuse you. Rule number 2. And this is the one where we were measuring angles between poles and different real line segments. This says that real axis segments in the z-plane belong to the root locus if there's an odd number of poles and zeros to the right of that real axis segment. And if that's the case, then that point or those points on that real line segment have an angle of minus 180 degrees. That's what we've also said. Here I'm just capturing these rules for you to go home and read and ingest. Rule number 3. And this rule applies when more than one branch of the root. So here, in this case, we're breaking everything today in class, apparently. But in this case, how many root locus branches do we have? In this example, how many root locus branches do you see? And I shouldn't have even drawn the arrows. Without the arrows, it might have been more confusing. But you have 2 poles. Each pole has to initiate a branch. And one branch is going left, one branch is going right, and they're going to collide in the middle. But rule 3 works only when we have these kinds of scenarios. When we have one branch of the root locus lies on the same real axis line segments. Okay? And these are called breakaway and reentry points. In this case that I'm illustrating above, in this parenthetical comment, this would lead to a breakaway point because K is increasing until they meet in the middle and then they break away from the real axis. We may have a case where they actually have left the real line and then they move around in the z-plane and then they come back and re-enter on the real line. So we have two possible scenarios. Sometimes they both exist, sometimes just one exists. One situation. We might just have re-entry points. In this case, we would just have a breakaway point. In some cases, we have both. And that was in our earlier root loci. On the one on the left, we have a breakaway point between 1 and 2, and we have a re-entry point to the left of the origin. Is that clear? The one on the right, what do we have? Breakaway, re-entry, or both? There we just have a breakaway, don't we? That's rule number 3, and we'll figure out how to use that in our discussion in a little bit. Let's go back to this particular example. Example number 2, I guess. We now have a a pole at the origin, and now we're going to calculate where these values are that allow us to find stability, the range of K for stability. And we have a pole at 3/2, an open loop pole at 3/2. You already know how to sketch it. Where are they going to meet? Where are these, how many branches do you have? How many root locus branches do you have in this example? How many open loop poles do we have? 2. How many root locus branches do we have? 2. So now the 2 are, one's going right, one's going left. Where will they meet? When we just have 2 poles, it's easy. They meet halfway between each other. When we have multiple poles, it's not always going to be right between them. Okay? But here they meet halfway between, so now it's going to be at 3/4 is where they're going to meet and collide. So we have 2 branches, and maybe what I should say here is which real axis line segments let's say belong to the root locus. So we have 2 branches, but in this case we have 3 real axis line segments that have been identified or created by those 2 poles. And now we want to know which of those 3 actually have the root locus living on them. Do you see that we have a real axis segment between 3/2 and infinity, a real axis segment between the origin and 3/2, and a real axis segment between the origin and minus infinity? We have to identify which of those 3, or all of those, or none of those, are a part of the root locus. And we use our phase angle condition to do that. And we've done that so many times that this is almost trivial to sketch this root locus. But now let's try to find these values for stability, if we're okay with this so far. So what's the lower limit? We've already done this multiple times, but let's go through it now formally. Lower limit on the value K for stability. Do you see how, picture-wise, do you see where we want to go or what that requires? Question? Yes. Yes. So the question was, if we have two branches, what are they, or where are they, maybe, is the question. We now have a branch here, and whether I go up or down is immaterial. Let me just say that that branch goes up. Then we have a second branch that starts here, and it obviously has to go in the conjugate direction as the previous one. But those now, yellow and blue, are the branches, the two branches of the root locus. And now what we're concerned with is how do we determine the stability bounds as we adjust K if this G of Z is now in a closed loop configuration with K in the forward branch. And we're now trying to find the lower limit on K, which is really now dealing with when do we simultaneously have all of our closed loop poles inside the unit circle. For what values of, or what range of K is that possible? Or is it possible for this example? That's the question we're answering now. So in this case, do we start with K equals 0, do we start stable? Is our closed loop system stable? No, because we have a pole at 3/2. So we know that the lower limit on K needs to be bigger than 0. And in fact, it's going to be when we reach that square, that's the limit on stability. We probably don't want to be having our system with a gain equal to that value to get us just to Z equal 1. We probably want to crank up the gain to get it further inside the unit circle. But the lower limit on K is dictated by that pole at 3/2 moving to the left. And we want to move it far enough to the left to get it on the boundary of stability, which is right on the unit circle at Z equal to 1. So now let's find out how we can do that analytically. T sub C of Z is our closed loop transfer function, and the denominator of that is 1 plus K G of Z equaling 0. And we know what G is. We have 1 plus K over Z, Z minus 3/2, and we're going to set that equal to 0. But we know then that we have K over Z, Z minus 3/2, that equals minus 1, or that equals 1 at minus 180 degrees. Or this is now suggesting that that equation really has two pieces to it. We have a magnitude piece and a phase piece, or an angle piece. The magnitude condition is what we are going to use to actually find a formula for K. We know that the magnitude of that left-hand side is a complex, we know it's a complex number. For complex values of Z, that left-hand equation is going to be a complex number. We know the magnitude of that has to equal 1 on the root locus, or to give us our poles, our closed loop poles. Or we're now saying the magnitude of K, Z, Z minus 3/2, that equals 1. Is that clear? And we're going to go ahead and just keep K being non-negative, so that that allows me to say, oh, forget the absolute value sign upstairs. I'm just assuming K is non-negative. So now let me just say the magnitude of that quotient is equal to the quotient of the magnitudes, and K is non-negative, so that I can now say that, oh, this is now Z times Z minus 3/2, that equals 1. Are we okay with the algebra that I've performed so far? And now I can simply multiply both sides through by the magnitude of the denominator. Or this now says that k is equal to the magnitude of z times z minus 3 halves. But again, that's just the magnitude of z using the magnitude of a product as the product of the magnitudes. I now can find the magnitude of z and multiply it by the magnitude of z minus 3 halves and end up with a gain of k. You give me a z, I can find a k. Right? I can find you the k that would correspond to that value of z. And what z are we interested in for starters? One value of k, or one value of z, or z equal to 1? Z equal to 1 is what we're interested in, because that's going to be our lower limit for k. So now, if we use this formula, this is our formula for k, and it came from the magnitude condition. We now want to say, what's k when z is equal to 1? So that now we have the magnitude, whoops, let me go ahead and do it in long form. We have the magnitude of z, and we have the magnitude of z over 3 halves with z equaling 1. So that this is 1 times 1 minus 3 halves. That's just a half, right? So that now we know that when k is equal to 1/2, one of those poles, we're going to have a value of z equal to 1. And we could then compute that. We could say, okay, what are the closed loop poles when k is equal to 1/2? Well, the closed loop poles are given by that formula. Or we now have 1 plus k over z, z minus 3 halves equaling 0. And what determines the closed loop poles? This, I'm getting back to the ratio of ratios. The numerator of this expression, right? This came from the denominator. Now I need the numerator of that denominator. So the numerator of that equation is when it vanishes. We're interested in what values of z cause this to vanish. So we now have z times z minus 3 halves plus k equaling 0, but we're interested in when k is equal to 1/2. Or this now says z squared minus 3 halves z plus 1/2. We want to know what are the roots of that quadratic. But we sort of can cheat. We know what one of those is. We found k equal to 1/2 when z was equal to 1. So we know one of the roots is going to give us a factor that causes it to vanish when z is equal to 1. Or we could now, you could factor this, and you should be able to see that this factors into a z minus 1 and a z minus 1/2. So if you didn't know anything else, you just said, what are the roots? Oh, I can factor that. I have a root at 1 and a root at 1/2. And these now are our closed loop poles. When what? When k is equal to 1/2. So I now have z equal to 1 and z equal to 1/2. And those are the closed loop poles with k equal to 1/2. Is that clear? That's now the lower limit on k for stability. What happens if we crank up k beyond 1/2? We know what's going to happen because we've already sketched the root locus. That's what our closed loop poles are going to do, but let's go ahead and see how we can maybe analytically determine some of that information. What happens to the closed loop poles which is really just telling us what's happening with our root locus. as k continues to increase. Or now we're really just saying, if I now have this, that's my governing equation. I can put that into z squared minus 3 halves z plus k, and I could see what happens as I adjust k. But in fact, what I want to know, I'm sort of talking my way through this analysis, but here I want to say, is there a maximum value of k when the roots are still real? And you could answer that with a yes based on this root locus. I'm asking, what's the gain k to get me, or how much can I crank up the gain k and still have my closed loop poles remain real? Do you see that if I crank up the gain k enough to make me break away from the real line, I'll no longer have real poles, closed loop poles. So I'm asking, what's the sweet spot? What's the value of k to get me right to that point? And what I'm saying is I started at 0, I'm increasing k, increasing k, increasing k, and then what happens? Well, that was actually a relative maximum value of k on the real line, and that's what I want to now compute. And how do I find relative maximums? This is our calculus. Now we can take the derivative. We could find the derivative information on this equation or with this information. We now know that what? We have k equaling z times z minus 3 halves. Or this is now z squared minus 3 halves z. I now have an equation for k in terms of z. I want to maximize this with respect to z when z is real. And this one's not too hard to differentiate, is it? This is just a polynomial. What happens when I differentiate z squared? To z or not to z, right? You're probably already zing. Sorry. I do not need to encourage that. Yes. So now the question is, why do we care about this keeping them real? We just want to stay real. No, what we're doing is we're just trying to identify some key points or features in this root locus sketch. And one way to do that is say, what's the gain k to get me to that breakaway point? And I can find it analytically by doing this relative maximum calculation. And now I can set this equal to 0, and hopefully you can see that the z value, when this relative maximum occurs, is where we knew it was going to be. It's at z equal to 3/4. And if I now use that z in my formula for my k, which came from the magnitude condition, I now have z minus 3 halves. What if I now evaluate that at 3/4? Now I know that 3/4 times 3/4 or 9/16 will be the gain k to get me to that magic point or that sweet spot where I have a relative maximum. This is now going to be the relative maximum of k, the relative maximum of k when I'm on the real line. So we're not worrying about the second derivative. All we're doing is trying to find a minimum. We don't care whether it's increasing or decreasing from that max or min. We're just trying to find a max or min. In this case, we're finding a maximum. Okay. Now, what happens as we continue to increase K? What happens as K increases beyond 9/16? If we didn't already anticipate what was happening, we had a pole at the origin and a pole at 3/2. We've now determined that this guy goes to the right, this guy goes to the left from the phase angle condition. We've learned that they get exactly between each other at 3/4, and maybe now we don't know what happens. But we know if we continue to adjust or increase the K, that they can't stay on the real line. So where do they go? Well, let's now convince ourselves that in fact they do go, one goes straight up and one goes straight down. And to convince us of that, suppose that I now say, what happens if that's true, then that triangle needs to be on the root locus, correct? And what does a point have to be, or what does it have to satisfy if that point's on the root locus? The angle of all of the poles and zeros have to sum algebraically to -180 at that triangle if it's on the root locus. So now let's make some sketches. Now we're saying, oh, the angle from that pole to that triangle is this angle. Let's say theta P1. The angle from this pole at 3/4 to that triangle is theta P sub 2. But what do we know about basically the triangles created by this sketch? The hypotenuse on both are these dashed lines. And do we know anything about those triangles? What's the horizontal length of their bases? Are they the same? And they share a common 90-degree angle, do they not? And they share a vertical distance, so those are congruent triangles. Now that they're congruent triangles, what do we know? We know that those interior angles, those acute angles, that theta P1 is in fact that angle. It's equal. And now we know that yellow arc and theta P2 form what? Supplementary angles? I'm getting back to geometry or whatever. And what does that mean? They equal 180, right? They're this straight line. And that's what we wanted, was it not? So now we've concluded that by construction, we know that theta P1 plus theta P2 is equal to 180 degrees. So if I now compute the angle of G at Z equal to the triangle, what do I know? How many zeros do I have? Finite zeros. I don't have any, do I? I don't have any finite zeros. So I don't need to worry about the zero angles contribution. What about my poles? I now subtract those because they're in the denominator. I have minus the angle due to the pole at the origin plus the angle due to the pole at 3/2. But wait, by geometry, I know that the sum of those two add to 180, which now says they satisfy the phase angle condition and they're on the root locus. And now I've convinced myself that the root locus sketch that I've been playing with all night is indeed true. And if I want a point on that root locus, how do I find the gain to get me to that point? Now what's the next point I want to figure out? I've cranked up my gain to, was it 1/2 to get me to Z equal 1? Then I cranked it up to 9/16 to get me to 3/4, both of them equal. Now I want to crank it up some more. And how much can I crank it up? What's the real part of the, now I'm going to, again, be interested in, and now if I can sketch this, I want to know what's happening right there. Do I know anything about that point? I know its real part, right? It's at 3/4 because that's where they broke away. What's its vertical distance? Maybe I don't know that, but that's y. But I know the magnitude of that point is 1. So now I can solve for y. Once I have that z, I can plug that complex number for z into my magnitude formula right here and compute what the magnitude is to get me to that limit on stability. And we'll pick up at that point on Monday.